The lesson today is taking a look at acids and bases. This is going to be a two-part video. The first part looking at the properties and naming of acids and bases, and the second part taking a look at the pH scale and neutralization. So the first part is looking at properties of acids. So how do we know something is an acid? Well, the first thing, if you're looking at the formula, it is going to contain a hydrogen. All acids contain at least one atom of hydrogen. When an acid is put into water, it will produce hydrogen ions or H plus ions. So when you see an acid with the aqueous symbol beside it, you know that it is actually dissociated and is floating around in the water as its independent ions. So you'll have these protons or hydrogen ions floating around as well as the other component or the other part of the acid floating around as independent entities. All acids have a sour taste to them, so you can think about it when you eat an orange or a grapefruit. Those are acidic substances. They give you that sour taste. They also cause a sharp pain or a stinging feeling when you get them in a cut. If you've ever had a cut or a paper cut on your finger and had some lemon juice in it, you'll know exactly what I'm talking about. And another common property of an acid is that they're all good conductors of electricity. That's because when they are put in water or when they are in an aqueous state, they are charged ions, and charged particles conduct electricity very well. So more properties of acids. If we looked at their reactivity, they combine with many substances, but primarily react with metals and carbonates. So to give an example of reacting with a metal, we can take a look at zinc and the acid hydrochloric acid. It will yield hydrogen gas and zinc chloride. So we take a look, there's our metal. Anytime you have a metal with an acid, it's going to be a single displacement reaction, always producing a hydrogen gas and some sort of an ionic compound, in this case zinc chloride. When they react with carbonates, what's going to happen is you're going to have the acid, in this case hydrochloric acid, plus your carbonate, calcium carbonate. You will always have the production of a carbon dioxide. So if this were a reaction, you would see the bubbles forming. You would also have the production of water and an ionic substance, in this case calcium chloride. So how are acids made? There are very few acids that are naturally found. So most of them are made, especially by companies that are trying to mass produce them. So take a non-metal oxide. So any non-metal element combine with an oxygen, so in this case sulfur trioxide, and you combine it with water, you're going to end up with sulfuric acid. So SO3 plus water gives us H2SO4 or sulfuric acid. And that's one of the reasons why carbon dioxide emissions from cars are making acid rain, because carbon, a non-metal with an oxygen, carbon dioxide, with the water in the atmosphere and with the rain, gives us carbonic acid. Okay? In terms of why they're important for the chemical industry, one, they're really reactive. So they're used as a catalyst. They start off a lot of materials. So they're used to kind of get a lot of reactions going. And they're also used as fertilizers in explosives, refining oil, electroplating metals. But a lot of things, if you need a reaction to occur, it's often acids that will kind of get it going. So how do we name them? There are two major classifications of acids. There are binary and oxyacids. Binary means that it contains hydrogen and one other element, and oxyacid implies that there is oxygen. So if we look at binary, what you would do is you would add the beginning, hydro, plus the name of the element it's combined with, changing the ending to ic, and acid. So for example, if we had hydrogen and fluorine, we would call it hydrofluoric acid. If we had hydrogen and sulfur, we would call it hydrosulfuric acid. Now, when we have these oxyacids, hydrogen plus a polyatomic ion. So any of those polyatomics that had oxygen in them, so phosphate, carbonate, we would have the name of the polyatomic ion, changing the ending to ic, and adding the word acid. So for example, if we had the nitrate ion, we add some hydrogen in front of it, we would call it nitric or nitric acid. Carbonate combined with the hydrogen would be called carbonic acid. Acetate would become acetic acid. You can see the pattern. So let's take a look at bases. Sometimes bases are called alkalines, but that's for a specific type of base. Those are bases that dissolve in water. Not all bases do, so we can't use those terms interchangeably, but sometimes it is, so just be aware of that little definition there. So in terms of bases, there are kind of two ways we can define them. Is they either produce a hydroxide ion, or the OH negative, when they're dissolved in water, or they have the ability to accept hydrogen ions or protons. Most commonly, you'll see bases with a hydroxide, but there are some bases that don't have a hydroxide but have the ability to accept the protons or the hydrogen ions. Either would qualify a substance as a base. They're all, most bases, are water soluble. When you put them in water, they're going to dissociate, just like we saw with our acids, into their individual ions or components. They all have a slight bitter taste to them. If you've accidentally had some sodium bicarbonate, you know that taste. It's not very nice. It's not very pleasant. When you dissolve them in water, they're all going to feel very slippery. Most cleaning solutions and soaps are bases. That gives them that kind of slippery, slimy feel. If you think about bleach, if you've ever done laundry and got a little on your hands, that's what gives it the slippery feeling, is that it is a base. And they, just like acids, are good conductors of electricity because when they're in water, there are charged portions to it, and therefore the electricity or the electrons can be conducted or moved through that substance very easily. So in terms of reactivity, bases react with acids, and they have the ability to break down proteins, or kind of their two major reactions they are involved in. So when we have acids reacting with bases, we end up with salt and a water. So hydrochloric acid plus a sodium hydroxide would result in what we know as table salt, sodium chloride, and water. And they have the ability to break down proteins. So it goes along with that reacting with acids because proteins are made up of amino acids and they break them down. That's why a lot of our cleaning products are bases, because they can break down proteins. So whether that is blood or other bodily fluids, but a lot of the things that we spill and that stain, like grape juice and things like that, it's the protein that causes the stain. So bases make really good cleaning materials because they can break those substances down. So how is it that we make a base? In this case, we take a metal oxide. So one of the metals combined with oxygen as a compound and combine it with water. So for example, sodium oxide and water will yield the base sodium hydroxide. Na2O plus H2O will yield NaOH. So why are they important for industry? The big thing is they can break down proteins or large molecules into smaller molecules. So for example, in terms of a drain cleaner, you have a clog in the drain, lots of hair, blocking the flow of water. You put a drain cleaner down, it is going to be able to break that substance down into smaller pieces and allow for the free flow of water. So mainly for kind of cleaning substances. But one of the things to keep in mind is because it reacts with proteins, you have proteins in your eyes. So if you were to splash some of the base in your eye, they can react with that protein. And a lot of times cleaning products can cause blindness because they're breaking down the proteins in your eyes. So always be careful when you're using a bleach or Drano or any of those other cleaning products. So how do we name bases? Most of them are ionic compounds that contain either a hydroxide, a carbonate, or a bicarbonate ion. Ammonia is the exception, because remember we said before a base could also be a proton acceptor. Well, ammonia can accept a hydrogen and become ammonium. But most of them, when you look at them, will be a metal and a hydroxide, or a metal and an oxide, or a metal and a carbonate. So for example, sodium hydroxide, calcium hydroxide, ammonium hydroxide. And then moving along to ones that contain carbonates, you will see sodium hydrogen carbonate or sodium bicarbonate, which is our baking soda. So how do we come up with the formulas? Well, all acids begin with a hydrogen. So that's how you identify whenever you see a formula. Look at it first and then ask, is it just a nonmetal with it? Or is it a polyatomic ion? If so, it's going to be an acid. A base, you're looking for that hydroxide ion, or you're looking for that bicarbonate, or just a simple CO3 carbonate to be a part of it. So this is the beginning of the second part of our lesson, pH and neutralization. So this is on the back of your note template. So when we're talking about pH and neutralization, indicators are used to tell whether something is an acid or a base. So an indicator is something that's going to change color in response to the concentration or the presence of either hydrogen ions or hydroxide ions. Some of the common ones that are used is red litmus paper and blue litmus paper. Red will always be red in in acids, and it will turn blue in a base. Blue will always stay blue in bases, but will turn red in an acid. I remember it B and B, blue for bases. Okay, red with a D, acid ends with a D. There are some indicators, however, though, that won't just tell you acid or base. They can actually tell you how acidic or how basic something is. That example would be a universal indicator, and it actually has gradations of color that will indicate how acidic or how basic. So there are 4 common ones that you need to be aware of because they will be used in many labs in grade 10 as well as grade 11 and 12. The first is bromothiamyl blue. When it's in an acid, it is a yellow or a greenish color. In a base, it's blue. So it still follows that rule, blue for base. Phenolphthalein is a colorless liquid in an acid, but turns pink or a bright fuchsia color in a base. It is either or. It is either colorless or it is pink. There are no gradations, whereas the bromothiamyl blue does kind of have some gradations throughout. Red and blue litmus paper are either or, acid, base, no gradations throughout. Red in acids, blue in bases. Same for the blue. It's always red in an acid or a blue in a base. Sometimes they kind of look a wet color. That's just because it has absorbed some of the water as part of its indicating job. So when we talk about the pH scale, what are we actually talking about? We're talking about a scale that is measuring the relative acidity or basicity, alkalinity, of a solution. So how many hydrogen ions are present, or how many hydroxide ions are present. So the pH of a solution is going to be either between 0 and 14. Okay, so within that range, we have incredibly acidic and incredibly basic substances, with the middle being 7 or neutral. So if a solution is between 0 and 7, it is going to be acidic, indicating that there are more hydroxide ions, there are more hydrogen ions than hydroxide ions. So acidic solutions have a lot more hydrogen ions. pH of 7 means it's neutral. It has a balance. It has even concentration of hydrogen and hydroxide ions. Basic solutions are anything greater than 7 and up to 14, meaning that there are more hydroxide ions than there are hydrogen ions. So the pH scale is a logarithmic scale, and what that means is each number is 10 times greater than the previous number. So if you were looking at the scale here and we said coffee has a pH of 5, it is acidic, whereas orange juice has a pH of just under 3. Well, each number here is 10 times greater than the one before. So coffee is 100 times less acidic than orange juice. Okay? If we look at gastric juice or the acid in your stomach, it is roughly 10 times more acidic than orange juice. Okay? Same thing goes with the bases. If we look at our regular cleaning detergents, most of them have a pH just under 11, okay? But bleach is just over 12. So bleach is more than 10 times more basic than a regular detergent, okay? That's what it means to be a logarithmic scale with a base 10. So in terms of examples, I'd like you to pause the video, make sure you get these down. We want to make sure that we indicate that acids are from 0 to just under 7. 7 right on is neutral. Bases are anything greater than 7 to 14. Acids can be broken down into strong acids, which easily give up their hydrogen ions, and weak acids, or weak bases and strong bases. Okay? Make sure you get some of those common examples down as well. So acids and bases, when they react together, participate in what is called a neutralization reaction. And there will always be 2 products, water and salt. Okay? Water, which is neutral, hence the name of neutralization reaction, and the remaining elements will produce a form of a salt, an ionic compound. So for example, if there's hydrochloric acid, or HCl, plus a magnesium hydroxide, your base, you will get the water, H2O, and magnesium chloride. That is the salt in this case. Okay? Acid plus base will always yield water and a salt. However, if the base contains a bicarbonate or a carbonate as part of its compound or part of its formula, carbon dioxide gas will always be produced as well. So you'll have water, salt, plus carbon dioxide. Okay? You'll recognize neutralization is simply a special type of a double displacement reaction. So write the balanced chemical equations for the following acid-base reactions. Can you predict what the products will be, and can you balance it? Pause the video now and give it a try, and we'll put the answers up in just a moment. Okay, so let's see how you did. Hydrochloric acid plus potassium hydroxide is going to yield potassium chloride and water. No need to balance, it's already balanced. If we have sulfuric acid plus lithium hydroxide, we're going to get lithium sulfate plus water. Okay, now notice in this third one, we have a bicarbonate ion. So we know there has to be water, salt, and a carbon dioxide produced. Sorry, I forgot that we still had to balance number 2. We had to put 2's in there to balance example B. In example C, you're going to get your water and salt plus your carbon dioxide. Okay, so these are a little bit tricky. You're going to take off that carbon dioxide, getting your CO2, and you have to take the other components to come up with your water and your salt. Okay, that's it for this lesson.